Ever wonder how a machine learns to make a choice? Not just crunching numbers, but actually picking one thing over another. It's one of the most fundamental ideas in AI, and today we're going to pull back the curtain and see how it works.
You see this every single day. Your email client deciding what's junk, your phone tagging your friends in photos, your favorite shopping app suggesting a new shirt. Computers are constantly making these little judgment calls. But how do they actually decide? How do they look at something and put it into the right bucket?
Well, it all starts with framing the problem in just the right way. We're not asking how much or how many. We're asking a much more specific question: which one?
And that brings us to a really key distinction in AI. On one hand, you have what's called regression. That's when a model tries to predict a number on a continuous scale, like the price of a house. But what we're talking about today is classification. This is all about picking a label from a list. Is this a cat, a dog, or a rooster? That's the core question, and it's how AI makes a choice.
Okay, so how does an AI go from just looking at raw data to confidently pointing its finger at one category? The secret ingredient is a really elegant mathematical tool that acts like a probability machine. You see, when a model first processes something, let's say an image of a sneaker, it doesn't just immediately say, "That's a sneaker." Nope. First, it spits out a bunch of raw, kind of messy scores for every single category it knows about. These are often called logits, and on their own, they don't really mean much to us. And that's the million-dollar question, right? How do you take that jumble of raw scores and translate it into something useful? Into a clear, confident decision.
That's exactly where the softmax function comes in. I love this thing. Think of it as a squishing machine. It takes all those raw scores, good and bad, and squishes them down so they all fit neatly between 0 and 1. And here's the magic part. It makes sure they all add up to a perfect 100%. It turns that messy chaos into a clean, understandable probability for each choice.
So how does this magic actually work? It's a pretty simple three-step dance. First, you exponentiate. It's just a quick math trick to make sure all the scores are positive numbers. Second, you add all those new positive scores up to get a grand total. And finally, you just divide each individual score by that total, and boom. Just like that, each score is now a clean, easy-to-read probability.
And the result is something like this. After our raw scores have been through the softmax ringer, our model can now say, okay, there is an 85% chance this picture is a sneaker, a 10% chance it's an ankle boot, and only a 5% chance it's a sandal. Suddenly, the right answer is crystal clear. But of course, a model isn't just born knowing what a sneaker looks like. It has to learn. So let's take a look at how that actually happens using a classic data set from the world of fashion.
For this, we're going to use something called the Fashion MNISD dataset. It's basically the perfect playground for teaching a model. We've got 60,000 tiny, simple black and white images of clothing, all neatly sorted into 10 different categories. It's the ideal little sandbox to teach an AI the difference between a pullover and a dress.
Now, the real key to learning anything is getting feedback, right? When the model gets an answer wrong, it needs to be penalized. This penalty is calculated by something called a loss function, which is basically a way of telling the model just how wrong it was.
For this kind of classification, our go-to penalty is called cross-entropy loss. A really great way to think about it is as a measure of surprisal. So if the model says there's only a 1% chance the image is a t-shirt, and it turns out the correct answer is a t-shirt, well, the model is going to be very surprised. And that big surprise leads to a big penalty, which forces it to adjust its thinking and be less surprised next time.
Okay, so we've trained our model. It's been working hard on our nice, clean, organized data set, and it's getting great scores. We're ready for the real world, right? Well, the real world is rarely that neat and tidy, and that's where things get really tricky.
This is without a doubt one of the biggest challenges in all of machine learning. The perfect, sterile world inside the training data is almost never a perfect mirror of the messy, chaotic, and constantly changing real world.
Let me tell you a classic story. The U.S. Army once trained a neural network to detect camouflage tanks in forests. They fed it pictures of forest with tanks and pictures of forest without tanks. And it worked. It got perfect accuracy. They were thrilled. But it was a complete and utter failure. It turned out that by pure coincidence, all the photos with tanks had been taken on a cloudy day, and all the photos without tanks had been taken on a sunny day. The model hadn't learned to spot tanks at all, and had just become a world-class weather detector.
And this isn't a one-off thing. Here's another one. A startup was developing a blood test for a disease that mostly affects older men. To get their healthy control samples, they just took blood from young college students. And surprise, surprise, the model they built was brilliant at telling the difference between an old person and a young person, not at actually detecting the disease.
Both of these stories are perfect examples of a critical problem in AI called distribution shift. It's what happens when the data your model was trained on is systematically different from the data it has to deal with out in the real world. It is a massive reason why models that look amazing in the lab can fail spectacularly in real life.
Understanding this challenge is absolutely crucial for building AI that's robust, reliable, and actually responsible. And this distribution shift problem, it's not just one thing. It actually comes in a few different flavors.
Let's break them down. First, you have covariate shift. That's when the inputs themselves change, but what they represent stays the same. Think about training a model on real photos of cats, but then testing it on cartoons of cats. Same concept, different style. Second is label shift. This happens when the frequency of your categories changes. Maybe a particular disease suddenly becomes much more common. And finally, you have concept shift, where the very definition of a category changes over time or by location. A great example is what people call a soft drink. Is it soda, pop, or Coke? The right answer completely depends on where you are.
So let's bring this all together. At its heart, classification is all about choosing which category. We learned the softmax function is that elegant engine that turns a model's raw hunches into clean probabilities. Models learn from being surprised by their mistakes. But honestly, the biggest takeaway is this. None of that matters if your training data is a poor reflection of reality. This huge problem of distribution shift teaches us that building great AI is often less about writing fancy algorithms and much, much more about deeply understanding the data that fuels everything.
And that leaves us with a final question to chew on. When an AI fails because the world it was trained for is no longer the world that exists, who's really responsible? Is it the data's fault, the developers, or is it just the unavoidable consequence of a world that simply refuses to stand still?